Yeah, howdy, folks. I'd like to share with you the formulas about the energy conservation of space, time, matter, and energy. And I've been thinking about it for a couple of days now, and I may have found what I was looking for. But to show you that, I show you a little thought experiment, which Einstein very much used as an instrument. And I use the same principle to perform a thought experiment in order to find the mathematical relationships between parameters. Well, I did the same thing, and I came up with the next thing. I'll show you. One moment. Here it is. Keep my hand stable. Suppose you have two masses that are linked together, mass 1 and mass 2, linked together by an energy source. And at t that is smaller than t0. The mass 1 and mass 2 are linked together, and the total mass, these and these, is m00. And the masses are identical. The masses are identical, the lengths are identical, etc. Now, what happens if you add energy or release energy? Suppose that is an explosive or something, or an energy source which drives apart these masses. They're equal. So what happens at t0 when the explosion is taking place at t0? So there is energy released. And what happens is that the energy release is the kinetic energy of both mass m1 and m2 plus a certain kind of loss. I mean, you have always an energy loss in heat loss. Heat is generated, light may be generated, so there is an energy loss. But at this t0, the lengths are still the same, and the delta t's, the passing of the time, is still the same as a still standing observer, just as it is here before the whole process is taking place. So delta t1 and delta t2 is the same as delta t0 of a still standing observer. Since they're not moving, but at this moment the explosion starts taking place, and the acceleration A1 and A2 are taking place. Well, if you look after a while, then you get this situation. T now, if you take T now, is T now 1. And in that in between this time and this time, some time has passed, but also the objects have moved. So a delta x1 and a delta x2, which we assume that they are the same because the masses are the same and the energy release is in between, so that it gets distributed over the two masses in an equal amount. And the velocity of v1 is the delta x, this portion, this amount of space, divided by the t now minus the starting point. So delta x divided by t now minus 0. That's the velocity. That's we as a viewpoint from a non-moving observer. That's us. That's the speed. The delta x divided by the delta t. The same goes, of course, for here, but then in the opposite direction. Now, here you have the energy, the kinetic energy of this mass E1 is half times the mass of that is now, because you added energy. So by having extra energy, kinetic energy, the mass has increased according to m now is m01. Sorry, I wrote it wrongly. I have to correct it. M1 now divided by the gamma factor, or multiplied by the gamma factor. The gamma factor, of course, is gamma is 1 over the square root of 1 minus v squared divided by c squared. And in this case, the v is Vm1. And in the other case, it's Vm2, which in this situation, because we have identical masses, are equal. That's what we assume, because both objects gain the same amount of energy, since it is a symmetrical situation. But now it has a kinetic energy of E is a half times m1 now times the Vm, the velocity of m1 squared. What also happens is that because it has a higher velocity, that the dimension is shrinking. So L now 1 is L1. Sorry, again, the same answer. L1 when it was here in the starting position times the divided by the gamma factor, which is this, is then L0 divided by gamma. And here it is M01 times gamma, which also goes for the M2, of course. So is M02 times gamma. And here is L02 divided by gamma. That's the formula for the Lorentz contraction. A similar thing happens for the delta t. So the time passing is elongated by also times the gamma factor. So t0, delta t0, times the gamma factor. Now, this is all known, this is all factual, and this is what Einstein also and Lorentz has found. But now, I stated that there is a conservation law going on here, because there is an energy input which results in a length contraction and a time elongation, or a Lorentz contraction and a time dilatation, and the mass is increased because you added energy. Okay, this is summarized in these formulas. Let me put it this way. And there you also see the relationship between all these things, that L, the length, is contracted by dividing by the gamma factor. The gamma factor is, of course, this. Gamma is 1 over the square root of 1 minus V divided by C in squared. The time is elongated by the gamma factor. The mass is raised or gained mass by the gamma factor. And the kinetic energy is E times half times m v squared. But m, of course, is m0 times gamma factor times the gamma factor. So the gamma factor can be expressed as E, the energy, divided by a half times m0 times v squared. But if you work it out, you get L is the L0 divided by E over a half times m0 v squared, in which results in L divided by L0 is, in the end, half times m0 times v squared divided by E. Well, the same goes for the time, and the same goes for the mass. So now you have expressions of the dimension, the space dimension, and the time dimension expressed in energy terms, in terms of energy. And that goes for the length, that goes for the time dilatation, it goes for the length contraction, Lorentz contraction. It can all be expressed as in terms of energy. So basically, what we also already knew is that energy is m times c squared. But now we also have that the dimensions, the space dimension and the time can be expressed as in terms of energy. a change of energy. So that means that also the space and time, just as mass, is a form of energy, and that's the conservation. It's governed by this type of conservation law that relates energy to space, but also to time. So energy, or space and time are also can be expressed in energies, which very clearly shows us. Let me which very clearly shows us that also space and time are related to energy and is a form of energy. You see that also with gravitation, where there is a lot of mass, like an Earth, like a star, like a neutron star, like a black hole. You see that the time dilates just as you speed up stuff, but also that the gravitational, the space dimension is altered. That's why space is bent, and so they're all related. Space, time, energy, and mass, they are actually different forms of the same thing, which is energy. So also space and time is a form of energy, and that's the and so it's governed by a conservation law, because you cannot create or destroy energy or mass, but apparently also you cannot create space, you cannot create time, or so it's all conserved, which in this way is related altogether. It's one and the same actually, but and it can transform apparently to different forms. If you have a lot of mass, you can bend, or you can how to say, reduce the space, and you can also elongate the time. So the presence of a lot of mass or a lot of energy goes at the cost of the time spent or the space that is occupied. And that's actually what I wanted to state, and this is clearly shown in these relationships, these mathematical relationships. Okay, this is what I want to share, and this is what my conservation law of space, time, energy, and mass is all about. And so space-time, it's actually basically energy. Just as Einstein found that mass is equivalent to energy, so also space and time are equivalent to energy and mass. This is what I want to share. Thanks for watching, and see you next time. Thanks. Hasta la basta.